Can you?
Yeah.
Yeah. So you know it's wide, right?
Yeah.
Okay.
Yeah.
No, that's kind of a sad reflection.
This is a very empty class.
Those of you who have no idea
Yeah.
what Casey's talking about, ask him afterwards.
Here we go.
Okay. So, here we are. Last class. So it's going to be really laid back. I'm not going to talk about much at all that I want you to know, so fine. But what I really want you to take away from today, we're going to talk a little bit about electromagnetic waves. And there are a couple of things I kind of want you to know about this, but what I really want to take you away from today is a sort of synthesis of stuff we've covered over the past 3 months, setting aside thermodynamics, but all of the electricity and magnetism. And really just to kind of take away some appreciation for kind of rather beautiful world we happen to find ourselves in, where electricity and magnetism behave the way that they do. And of course, as we're just starting to see, also basically explain for us what light and everything else in the electromagnetic spectrum is. So I really want you to kind of leave today, leave this course, with an appreciation for those things. Just kind of yes, sir.
What's your cover today class being
Okay, back to the mundane stuff. Will the stuff we're covering today be on the final?
That will be on the front of your bike.
What's your preferred answer to this question?
No.
Okay. All right. I won't ask you anything on today's material on the final. That doesn't mean you shouldn't know it. All right. So we're probably going to end early unless I just wax lyrical for the next 60 or 70 minutes. So the first thing I want to do is just show you a few little cartoon applets. You'll have seen, particularly earlier in the semester, I referred you periodically to a site that I like quite a bit for things to do with electromagnetism. This person, some individual who made some apps many years ago now that illustrated various phenomena in physics, and in particular there's a lot of stuff on there with electromagnetism. And it's just really nice at this point to go back and play around with this stuff, and I'm going to do that with you in a while. Just because it's a really nice visual reinforcement of the stuff that you've been learning. And it's particularly useful, I think, when it comes to magnetism, because, right-hand rule and all this stuff, it's quite easy to get lost. And so seeing this visually, I think, can be really helpful in kind of having it sink in. So, I'm going to show you a few of those applets, to do primarily with magnetism. We're going to come back and talk about electromagnetic waves. We already described them a little bit on Tuesday. I'll pick up there, describe a little bit more about the characteristics of electromagnetic waves. Talk about the electromagnetic spectrum. Somewhere along the way we have a couple of fun demonstrations. And then I'll talk a little bit about the energy and momentum carried by electromagnetic waves. Okay? So let's see where that gets us. So, we turn down the lights. Okay, so this is going to go up.
These purple pictures and light.
All right, so this is the site that I mentioned. I'm just going to sort of somewhat randomly pick a few things here to do with electromagnetic waves. And as you see, this is already showing things to do with mechanics. And for those of you going on to do third semester physics with wave phenomena, this section here again is very useful, I would say. Just as I'm scrolling down this, again, random thoughts, you see there's something here about Fourier analysis. For those of you going on to do particularly 2601, that's a nice thing to know about. All right, so here's the stuff that's really of interest. Electricity and magnetism, statics, and then electrodynamics. Oh, and the other thing I should say is, closing comments, I'm going to say a little bit about electromagnetism and special relativity. So here you'll see two captions, electrostatics and magnetostatics. Just want to mention what magnetostatics really means, because as you know, to some extent, magnetism is intrinsically associated with motion of charges inherently. So what does it mean when it says magnetostatics? What it really means is that it's a sort of steady state situation. And then dynamics, of course, in the lower set of all of this is when we've got things that are changing, and that's what we've been dealing with for the past day in lecture. So let me just remind you of a few things that we looked at with electrostatics. I'll be brief here. Oh, shit. Apparently I'll be very brief here. So why do I not have an internet connection? Let's see if I can get a hold of this one. Okay, let's try again. Okay. All right. So briefly, with electrostatics. Okay, I'm going to go to 2D. All right, so you saw this sort of stuff at the beginning of semester. So what you're seeing is the simplest possible sort of representation of electric fields here associated with a static positive charge. Arrows representing the field, in this case heading outwards from a static positive charge. Those white lines are supposed to be equipotentials. Okay, so you've gotten used to this sort of representation of electric fields. There's no attempt here really to have the arrows show anything about the magnitude of the electric field, but fine, you know how all that stuff works. So on electrostatics, I think the only other thing I'll show you here as a reminder is the electric field setup associated with a dipole. Okay, so plus and minus equal magnitude charge separated by some distance, and sorry, this is a little bit out of focus unfortunately, but you can see the arrows pointing in and out respectively from the negative and positive charge. Why I show you that is because in a little while when we talk about generation of electromagnetic waves, one of the simplest ways to do that is to take an electric dipole like this, perhaps more typically sort of continuous electric dipole, which might be set up by driving a potential across some macroscopic rod like this and flipping the polarity of this back and forth. So it would be macroscopic amount of positive charge, let's say up here, a macroscopic amount of negative charge down here, flipping this back and forth at some frequency. And that's one of the most common ways to actually produce electromagnetic waves. You're going to see a couple of demonstrations of that in a little while. So I just wanted to remind you of the electric field pattern associated with a static electric dipole. All right, so let's see what I got here. Magnetostatics. Okay, so these I'm going to be a little bit more, maybe go a little slower here to sort of show you a few things. So now, it's not entirely, it's particularly annoying because it's out of focus, but what this is representing is an invisible line of current that is moving into or out of, in fact you can figure it out if you view the sign of those little dots, which is supposed to be kind of things representing the direction of magnetic field lines. And so what you see here is there's a current line going into or out of the plane of the board in the center. And of course what you see is these things circulating around it, okay? Now in some sense here, the speed at which they're circulating is supposed to represent the strength of the magnetic field. And as you now know, this is wrapping around circular trajectories according to our right-hand rule. So that's a current line showing really the field associated with it. If I were to take two currents, one going into the board and one coming out of the board, we'll start to see something like this. So again, now you've got counter-rotating motion here, counter-rotating magnetic field lines associated with those two anti-parallel current lines. So that is a current line dipole. To show you what happens for a moving charge, of course this is really no different than a current, except we're just looking at an individual charge rather than the macroscopic amount of charge. And I apologize, the thing is not greatly in focus here. But that single charge now is not moving into or out of the plane of the board, but it's supposed to be moving upwards, okay? And again, the motion of those little white dots is to represent the field lines wrapping around that motion of the charge. So let's see what else I can put in here. A couple of things that we've been working on relatively more recently. A current loop, okay? So take a look at this. So the current loop now in a sort of horizontal plane represented by those yellow lines. Now you see the magnetic field lines represented by those white dots again. And this is a pattern that you're pretty familiar with now. It's what we would also represent quite often by a magnetic dipole, an associated magnetic dipole moment. So you're used to that. Let me show you what happens if I stack a bunch of loops. That's not the one I wanted. I wanted a solenoid, I guess. So now I'm stacking a bunch of those loops, and you see the superposition here, so that I get the same pattern from each loop, but they're all stacked, and so I get the magnetic field configuration that we've learned to associate with a solenoid. Okay? So in the center, turns out a rather uniform axial field along the axis of the solenoid, and then outside the field spreading out rather large distances is generally very weak. So that gives you an idea of the magnetic field associated with a solenoid. And then, though we barely touched on this, there was a little bit of this in lecture, and I think possibly one problem briefly on the homework. I can take my solenoid, grab its ends, wrap them around in a circle, and have them connect again, which will give me a solenoidal, toroidal solenoidal field. Okay? So again, the yellow here is supposed to represent a torus. Think of it as a bagel. And the surface of the bagel is where our current is wrapping around. This one's much harder to understand what's happening to the white dots, but if you can kind of trace one or two of them, they're moving around sort of within the bagel, okay? And all of these magnetic field configurations have important practical uses, which we've barely touched on, but lots of interesting stuff here. Okay, so that has to do with so-called magnetostatics, which is again where we got some constant current or constant charge motion, not any explicit change with time. And now what I'm going to do is just flag a few things that come into the electrodynamics. Let's see what we got here. The thing that's most of interest is maybe this one. Okay, so I'm just going to be brief on. This is again the sort of representation of taking an electric dipole and having it flip back and forwards, okay, with some frequency. And what you're seeing here are patterns of electric and therefore magnetic field that are radiating outwards from that oscillating dipole. So we're not going to do any of this quantitatively, but if you go on and do further electromagnetism, you'll often pick here and start looking at these sorts of interesting scenarios. What we're seeing in this case is a superposition effect. It's already fairly complicated. But most notably, it seems like the field waves that are traveling outwards are primarily, well, let's say they've got the largest amplitude, the largest strength, in directions that are perpendicular to the dipole axis, okay? So I'm going to show you a couple of demonstrations associated with that in just a moment, okay? So this is going to be our sort of basis for electromagnetic waves and generating them, and as we'll see, we can kind of also detect them making use of something similar. So, let's see what I want to do. I'm going to raise the light level for a moment. And just remind you of what we've learned about electromagnetic waves. And then I'm going to show you a demonstration that has to do with this. So, okay, I'm going to raise the light level here. Simultaneous oscillating E and B fields. So they are in sync. E is perpendicular to B, and both are perpendicular to the direction of wave travel. And as we learned briefly at the end of Tuesday's class, at least in vacuum, when this phenomenon is occurring, there's a prediction for the speed at which the wave is traveling, and has this remarkable characteristic that it is simply determined by the two constants, the permittivity and permeability of free space. So this actually turns out to be 1 over the square root of epsilon mu zero in vacuum. So the cartoon, I'm not going to try and draw it again, I'm just going to show you a representation of this again up on the screen. So take a look at this when I lower the light level. So this is a very slow-moving cartoon of a typical electromagnetic wave. Again, this is crappy, I apologize for that. So let's say, I can't even read if it's labeled, I don't think it is. Let's say that the red oscillation corresponds to electric field, and again, this is a sinusoidal wave. The easiest thing to start with, for reasons we talked about on Tuesday. So the red represents the electric field, sine wave motion. Perpendicular to it in blue is the magnetic field, and it's in sync, which means when I have zeros on the electric field amplitude, I have zeros on the B field. Conversely, when I have maxima on the electric, I have, conversely, similarly, when I have maxima on the E field, I have maxima on the B field. So they're in sync in that sense, and then if you look at this, the wave itself is moving along what I assume is, I don't even read this, does it say X? Anyway, that axis. And the whole thing is propagating in time. Okay, so this is what I want you to have as the mental image for your traveling electromagnetic wave. So, let me just now show you a couple of demonstrations of this. Two setups that are basically going to illustrate a similar phenomenon. I'm not sure if I'm showing both, but why not since we have the time. Okay, take a look at this thing. So basically a long piece of metal conductor. It happens to be in a loop shape, which is roughly speaking irrelevant. But let's just imagine it's a piece of metal like this. And what we're going to do is drive it with a sinusoidal current, or EMF, provided by this function generator. And all it's going to do is basically make charges oscillate back and forwards along this metal rod. So you've already seen now, you've gotten an idea of what this is going to do. It's going to start sending out electromagnetic waves, and preferentially it's going to send them out in these directions. That's where the signal is strongest. It's relatively weak in this direction. Now, fine, I'm driving charges back and forward. They are going to produce an electromagnetic wave. It turns out, in terms of the orientation of this thing, the electric field vector is going to be parallel to the moving charge, okay? So in this sense, we can imagine the electric field oscillating side to side like this. The wave itself is going to propagate this way, and the magnetic field is going to be oscillating vertically, okay? Now, this is leading into a topic that we don't have time to talk about in this course, but many of you have heard about already, which is the phenomenon of polarization of waves, and polarization of electromagnetic waves in this case, which is to say it's important in many cases which direction the electric field is oscillating in, and therefore which direction the magnetic field is oscillating in. Why is that? Well, what happens when those waves reach something else will depend to a large extent on the orientation of those E and B fields. So what I'm going to demonstrate for you is a phenomenon that you make use of every single day, possibly almost every single moment of the day, you guys on your cell phones and things, which is the transmission and receiving of electromagnetic waves, okay? So you can imagine, I energize this thing, I start driving charges back and forth, I'm producing electromagnetic waves, I can encode information with those waves. Maybe then I can pick them up and make use of that information. So what we have over here is almost the inverse of what's over there. So now I've got a freestanding metal rod, and if you look at the relative orientation, obviously they're parallel to each other. As an electromagnetic wave travels over here, think of the electric field component now. As it arrives, I've got an electric field which is going back and forwards in this plane. This is a conductor, so it has free charges in it. What do you expect is going to happen when I have an electric field, in this case a time-varying electric field, come along here and hit those free charges in this piece of conductor? What's going to happen? You want to go ahead, Hunter?
The charges are going to respond.
Right,
Yeah.
because there's a force on them, just Q times the electric field. So the charges are going to respond, they're going to experience a force, they're going to be accelerated. And of course, as soon as we've got charges moving here, it's setting up really basically a signal, a current if you will, that we can do something with. In this case, we can connect it to a sound generator, an amplifier, and see if we get a signal. So let's do just that. It's a pretty straightforward demonstration, but it's a little time to warm up. So what's happening now is it's generating a, sorry, turn this down a bit. Seems like it's, yeah, further down, okay, we good? All right. So, it's, so we've got something that's a sinusoidal signal back and forth here, and in fact, since it's being translated through a loudspeaker into sound, and it has a certain frequency, we can even say something about the frequency at which this thing is oscillating. I'm not great at picking up pitches, but this is pretty high, it's certainly still audible. So it's probably a few kilohertz, something like this. And so what's happening over here is we're driving charges back and forwards at a few kilohertz, it's sending out electromagnetic waves. They're being picked up here, the charges in this thing are being accelerated back and forth. That electrical signal is being pumped into a loudspeaker, which is vibrating back and forth at the same amplitude. Yeah, this is quite annoying, isn't it? All right, so let me show you a couple of things that are important about the pattern of the electromagnetic waves that are being sent out. First off, I mentioned this phenomenon of polarization, the fact that the orientation is important. If I take this thing and orient it so that it's not horizontal but vertical, what might you expect will happen?
It won't make any sound because the electric field is vibrating. they have very small movement charge.
Yeah, it's basically that I'm not able to move as much charge over, let's say, as much distance. That's a little bit of a weird way of describing it. If I orient this thing vertically compared to horizontally, so let's see what happens. Okay. So, in the good old days before you got all of your entertainment and everything sort of over the internet and wired connections, though I guess a lot is wireless these days. Of course, you had radios and TVs that worked on exactly this principle, okay? So you would have had connected to your radios and TVs a little antenna, which you would have had to orient in an appropriate way so that it lined up with the orientation of the transmitting tower, let's say. And also you want to point it in an appropriate direction. So that gives some indication of the phenomenon of polarization. And just to reinforce the idea that the transmission of the waves is strongest perpendicular to the axis of the dipole oscillating backwards and forwards, if I take this off axis, it's slowly going to decrease in amplitude. It's a fairly slow change as I come around here, and I can't do it all the way because the wire's too short. But if I had it right over here, essentially here, nothing at all. Okay, so it's somewhat directional. And obviously, we're going to make use of that also when we're trying to transmit the signals electromagnetically. Okay, I think I'm actually not going to show you the other variant of this, which is actually a true case of TVs picking up electromagnetic waves and showing you the variation as I change the orientation of the receiver compared to the transmitter. So I think I'm not going to do that. Let me just turn this one off. Okay, so we've learned a few qualitative things about electromagnetic waves. What you've seen here is an example of electromagnetic waves that are not visible to our eyes. You are not seeing light in this region, of course, but light is, of course, an example of electromagnetic waves. And so just to give you a sense of the entire electromagnetic spectrum, let's pull this up. We'll talk a little bit about this. Okay, so let's try this one maybe. Okay, I'm going to stick with this. So let me just talk about the whole possible range of the electromagnetic spectrum. So, generic electromagnetic waves. There's a lot going on this image, so let's talk our way through it. Again, my apologies, it's not in focus. So, what have we learned? First off, whatever these things are, synchronous electric and magnetic field oscillations, we know that in vacuum they have a unique travel speed, 3 × 10⁸ meters per second. But that doesn't say anything for us about the frequency and associated wavelength of the waves, okay? So, in fact, we can generate electromagnetic waves over the entire possible frequency spectrum, which is essentially infinite, and they will have corresponding wavelengths. Now, one thing that I mentioned briefly in Tuesday's class is it turns out there's a very simple relationship between these 3 key parameters that describe traveling waves: frequency, wavelength, and the speed at which they travel. Okay? So frequency is just how many times they oscillate in a given time interval. The wavelength is the physical extent between, let's say, one peak in that sinusoidal waveform and the next peak in the sinusoidal waveform. And then the velocity is obvious what it is. And the relationship is that the product of the frequency and the wavelength just tells me the wave travel speed. Okay? So in this case, the product of the wavelength and the frequency gives me the speed of light. So I can vary one, and the third of these things will vary dependent on how I change it, which means that for high frequency waves, I have a very short wavelength, and vice versa. So for low frequency waves, I have very long wavelengths. So up there, you'll see along the top of that fairly complicated plot, you'll see a representation of wavelength going from long on the left side to short on the right side. And there's some representations of physical objects in the middle of the plot that give you a sense of scale. Okay? So what we've come to call things like, for example,